Okay, see here. Here, this circuit shows the common base configuration of NPN transistor as well as PNP transistor. Now, in the case of NPN transistor, if you observe here, the current through the emitter is away from this transistor. It is away from the transistor. To satisfy the standard equation of transistor, IB, IC must be entering into the node. That means IE is equal to IB plus IC must be satisfied in the case of transistor. So here IE is away from the transistor. So that's why IB and IC both are entering into the transistor if you observe the circuit. Similarly, input voltage across this transistor is given by VEB. Here input is connected between emitter and base. So that's why input voltage is VEB. And output voltage is connected between collector and base. So that's why the output voltage is VCB, collector to base voltage. And if you want the supply for all this, we need to give supply voltage. That is supply input voltage as well as supply output voltage. If you observe the circuit, here there is no supply voltages. If you observe the circuit, here there is no supply voltages. If you are not giving supply voltages, means we are not going to get all these input currents as well as output currents, and the input voltage is input currents. Why? Because here we are not giving any supply. If you give the external supply, then only we are going to get the voltage across the transistor as well as current to the transistors. Now I am going to connect that input voltage as well as output voltage. Nothing but input supply voltage, output supply voltage. Now this VCC is called your output supply voltage, and here VEE is called your input supply voltage. Here VCC output supply voltage, VEE input supply voltage. Okay. Whereas VEB voltage across emitter and base in input side, whereas VCB is collector to base input voltage. Here the supply voltage is different as well as voltage across the transistor are different. Okay. Now this is related to NPN and this diagram is related to PNP transistor. Okay. Now coming to the equations related to this common base configuration. Now from this, actually I want to determine the characteristics. In the case of common base configuration, I am going to observe the input and output characteristics. Now here, this is your input characteristics as well as output characteristics for your common base configuration. Okay, if you want to draw this input as well as output characteristics, always the input characteristics are drawn between the input voltage versus input current. See here, this is VBE is your input voltage in the case of common base configuration. Similarly, IE is your input current for your common base configuration. If you observe here, VEB input voltage, IE input current. Okay, here the input characteristics are drawn between the input voltage on x-axis versus input current IE on y-axis. Whenever the output voltage is constant, already I written here. See here, if you observe here, input characteristics are drawn between the input voltage versus input current whenever the output voltage is constant. Similarly, output characteristics are drawn between the output voltage versus output current whenever the input current is constant. In all these characteristics, we are saying that input voltage, input current, output voltage, output current. That means first, before drawing these curves, we require the input voltage, input current, output voltage as well as output current. So that's why I am going to write all these equations by using this circuit diagram. Now here, if you observe this input circuit, this is input side, this is your output side. Now here, if you travel in clockwise direction in the input circuit, if you travel in clockwise direction, see here, VEE is your voltage drop, as well as across resistor also voltage drop, as well as across VEB also voltage drop. These all are voltage drops. These all are voltage drops. Now that's why I am writing this equation as algebraic sum of the voltage rises is equal to the algebraic sum of the voltage drops. Whereas voltage rises are not there, so that's why I am keeping it as 0. Okay. Now VEE, voltage drop, VEE, and after across resistor there is a voltage drop, but here the current IE is in opposite direction. Why? Because we are taking in clockwise direction. Here IE is moving in the anti-clockwise direction. Here both are in opposite direction here. Okay, so that's why we are going to take this as minus IE. Now it is minus IE into RE plus this voltage drop VEB is equal to 0. Now this is the equation from the input side. This is the equation from the input side. Okay, from this equation I want to write down the input voltage equation as well as input current equation. Input voltage equation as well as input current equation. Now here VEB is called input voltage. From this equation, VE is supply voltage, IE input current, RE current limiting resistor at input side, VEB input voltage. Now our requirement is this input voltage. Now VEB is equal to minus VEE plus IE into RE. See here. Input voltage. Input voltage is equal to minus VEE plus IA into RE from this equation. Okay. Minus VEE plus IA into RE. This is the input voltage equation. Similarly, I want to write the input current equation from this. Input current equation. Okay. Now I write this equation as IERE is equal to VEE plus VEB. If it comes to the RHS side, it will become positive. So that's why IERE is equal to VEE plus VEB. From this, you can write the equation of IE as VEE plus VEB by RE. Now this is related to input current equation, input voltage equation. Okay, now we got the input voltage as well as input current from this input circuit. From this input circuit, I am calculated this input current IG, input voltage VEB. I am saying this equation as equation 1 and equation 2. Now similarly, I want to write the equation for output voltage VCB and output current IC. Before writing those two equations, I want to write the KVL equation for this second loop or output loop. Okay. Now, in this case, I am assuming that current is flowing in the anti-clockwise direction. Current is flowing in the anti-clockwise direction. That means here VCC is your voltage rise, whereas RC voltage drop, VCB voltage drop. Now, voltage rise is equal to the voltage drops, and algebraic sum of the voltage rises is equal to the algebraic sum of the voltage drops in the case of KVL. Now here VCC is equal to IC into RC. Why? Because current to the RC is IC. So IC into RC plus voltage drop, because this one is VCB. From this again I am going to write the output current equation IC. Now IC is given by VCC minus VCB by RC. Now this is your equation 3. Similarly, I am writing the output voltage equation VCB. Now VCB is given by VCC minus IC into RC. I am naming this as equation 3 and equation 4. Now this equation is related to output and from the output loop. Okay, output current as well as output voltage. Okay, now one more. In addition to these 4 equations, I am going to write one more equation, that is output current equation in terms of reverse saturation current. Output current equation in terms of reverse saturation current. Okay, this is standard equation in terms of reverse saturation current. Here, if you observe this equation, equation third, in the equation that there is no reverse saturation current. Okay, if you want to consider the reverse saturation current, then you have to write the equation as output current is equal to the gain into input current plus 1 plus gain into reverse saturation current. This is the standard equation for all the configurations. If you consider the reverse saturation current, okay, once again I repeat this equation. Output current is equal to the gain, G means gain, and gain into input current plus 1 plus gain into reverse saturation current represented with IC naught. Okay. Now here I am writing the equation. Output current means in the case of common base configuration, what is the output current? IC is your output current. So IC is equal to gain represented with alpha and. In the case of common base configuration, gain represented with alpha. In the case of common emitter, gain represented with beta. In the case of common collector configuration, gain represented with gamma. I will explain this in future classes also. Now first see the common base configuration. Now output current is represented with IC and gain represented with alpha in the case of common base configuration, and input current in the case of common base is IE. See here, IE. So here input current is IE plus 1 plus gain means alpha, IC naught and IC naught. Now this is your output current in terms of reverse saturation current. Output current in terms of reverse saturation current. IC is equal to alpha into IE plus 1 plus alpha into IC naught. Okay. Now alpha into IE, alpha into IE. Instead of writing this 1 plus alpha into IC naught, I am representing this total as ICBO. Here ICBO represents that reverse saturation current. This not nothing but this 0. This 0 indicates the reverse saturation current in the case of CB, common base configuration. Here CB means common base configuration. In the case of common base configuration, reverse saturation current. ICBO means reverse saturation current in the case of common base configuration. And here ICB naught, since ICB naught is nothing but 1 plus alpha into IC naught. In some textbooks is going to write the equation directly like this. IC is equal to alpha into IE plus ICBO. Directly is going to write the equation as output current is equal to alpha into IE plus ICBO. Okay, but ICBO is given by 1 plus alpha into IC naught. Okay, these are your input current, input voltage, output current, output voltage in terms of output current in terms of reverse saturation current. These all are the equations related to your common base configuration. Total 5 equations. Okay, input current, input voltage, output current, output voltage, and here output current in terms of reverse saturation current. Okay, now I'm going to explain the input characteristics for your common base configuration. Now here, if you observe here, these characteristics are similar to your PN junction diode forward bias characteristics. Why? Because here the input is connected in forward bias. If you observe here from the circuit, the input is connected to forward bias. Why? Because here emitter junction is forward bias in the case of active region. Already I explained this in my previous class. Emitter junction is always forward bias. Collector junction is always reverse bias. Why? Because we have to connect the circuit in the active region. In the case of active region, the transistor is going to act like amplifier. So that's why the emitter is forward bias in the case of active region. So this is forward bias means here N type and P type is connected in forward bias. So this is looking like the forward bias of PN junction diode characteristics. That means up to certain voltage there is no conduction. If you apply the supply voltage up to the some 0.3 or 0.2 volts, there is no conduction. There is no conduction because of that voltage is 0. And after reaching that cut-in voltage, the current is going to increase like this. Whenever the output voltage is constant, this is a graph. This is a graph whenever the output voltage is constant. Okay, that means if VCB is equal to 0, initially I am keeping this VCB is equal to 0. Then there is no effect on input. Here VCB is equal to 0. There is no effect on input. So simply it is VCB is equal to 0. This is the characteristics. Okay. Now if VCB is equal to 8, that means here output voltage is constant. That is I am taking output voltage as constant. That is 8 volts. Because of that, the characteristics are shifted towards left side. That means the cut-in voltage is somewhat decreased because of this increased output voltage. Whenever VCB is equal to 0, this is shifted towards left side. Similarly, if you increase this VCB to the 18 volts, that means again the output voltage is constant at 18 volts. Again, this graph is shifted towards left side. Okay, this is your common base configuration input characteristics. See here on x-axis we are taking the input voltage, on y-axis we are taking the input current. Here, similar to your common base configuration. Similar to your PN junction diode forward bias. VBG or VGB in terms of volts, IE in terms of milliamps. Why? Because the emitter is highly doped material. So that's why I'm going to represent the current as in terms of milliamps. Okay, VCB is 0 volts, 8 volts, 18 volts. Here, the output voltage is higher voltage. Very huge amount of voltage is applied across this output. That is in terms of 0, 8 and 18 volts. Okay. When you increase the output voltage, the graph is shifted towards left side. Nothing but the cut-in voltage is going to decrease. Okay. Now see the output characteristics of your common base configuration. So here, before explaining this output characteristics, I am going to write the standard equation in the case of transistor. In the case of transistor, the standard equation is given by IA is equal to IB plus IC. I already explained this relation. IA is equal to IB plus IC. Emitter current is equal to the base current plus collector current in the case of transistor. This is the standard equation in the case of transistor in terms of current. Okay. Now here we are saying that IA is equal to IB plus IC. To explain this output graph, I am going to take this equation. Now here, output characteristics drawn between the output voltage versus output current whenever the input current is constant. I already written here. See here, if you observe here, output characteristics are drawn between the output voltage versus output current whenever the input current is constant. Here, what is output voltage? VCB. Here, output voltage is VCB. Output current is IC. Whenever the input current IA is constant. Okay. Okay. VCB on x-axis, IC on y-axis. Here also IC is in terms of milliamps. Why? Because here the IC is nothing but collector is moderately doped material or mediumly doped material. So that's why I'm going to take this IC also in terms of milliamps. So here VCB in terms of volts on x-axis, IC in terms of milliamps on y-axis. Okay. Output voltage versus output current. Whenever the input current is constant, that means IA as constant. IA is equal to, I am taking it as 0 milliamps, 0.5, 1.0, 1.5, 2.0, 2.5. Okay. From this equation, if you observe this equation, IA is equal to IB plus IC. Okay. That means, what is IB? IB is very, very, very less current. Why? Because when I explain the construction of your transistor, in that case, I already explained that the base is lightly doped material when compared to the emitter and collector. Always the base is lightly doped material. So that means very less number of recombinations are present in the case of base. That means very less amount of current present in the case of base terminal. The base is having very, very less amount of current. That is in terms of microamps. That is in terms of microamps. Whereas IA in terms of milliamps, IC also in terms of milliamps. Why? Because these are highly doped material and IC is moderately doped material. Whereas IB is very, very lightly doped material. So that's why the current is in terms of microamps. Sorry. That is in terms of microamps. That means we can write this equation as IE is approximately is equal to IC. If you neglect this IB, what will happen? IE is approximately is equal to IC. Okay, here. Whenever you are taking IE is 0 milliamps. Okay, here the IC also you are going to get nearly is equal to 0 milliamps. Nearly is equal to 0 milliamps. Here there is a small increase. If you observe the straight line, see here. Here there is a small increase. The small increase is because of this IB. Because of this IB, there is a small increase in current. Why? Because this is in terms of microamps. So very small increase of current. Similarly, if you take here, this is a 0 and this is a 0.5. When you apply 0.5, very small amount of current is going to increase. Similarly, when you take IE is equal to 1 milliamp, there is a small increase here. IE is equal to 1. Similarly, 1.5. Similarly, 2 milliamps. Similarly, 2.5 milliamps. Okay. Here, these are approximately equal. IE is approximately is equal to IC. 2.5, 2.0 to 1.5, 1.0. Approximately equal. IE is equal to IC. Okay. Here, these characteristics are going to move on left side also. This is due to the Edley effect. Here, this is due to the Edley effect. I will explain this Edley effect after completion of this common base and common emitter configuration. Okay. This graph is on negative axis also. This is due to the Edley effect. Okay, now here this is called active region graph. This is called active region graph. Okay, the graph below this is called your cutoff region. Okay, here the graph below is called your cutoff region. The characteristics below is called your cutoff region. In the case of cutoff region, both are reverse bias. That means both are approximately equal to 0. I'm going to represent in the downward of this characteristics. Okay. Now here, this is a cutoff region, whereas left side of this graph here, saturation region. Okay. Left side of this is a saturation region. The graph is called your active region. This graph is related to active region, and this is a cutoff region. This is a saturation region. Okay. This is about your input and output characteristics of your common base configuration. Okay. From this, we can give this input impedance, output impedance, current gain, voltage gain, power gain, and bandwidth. We can explain all this here. Here, input impedance. Impedance is ratio of voltage to the current. So here, input impedance is defined as input voltage to input current. So in this case, what is the input voltage? VEB is your input voltage. Input current is IE. So that's why it is VEB by IE. Here, VEB by IE. So here, this is medium. Here, the input impedance is medium. Why? Because the VEB is somewhat less voltage. IE is in terms of milliamps. Okay. So that's why this is a medium. Here, VEB is somewhat medium voltage. So that's why I'm going to take input impedance as medium. Whereas output impedance is defined as output voltage to the output current. Here, output voltage is in terms of VCB, output current is in terms of IC. So that's why it is VCB by IC. Here, VCB is very high voltage. Here, VCB is very high voltage. So that's why the output impedance is high. Output impedance is high. Input impedance is medium. Whereas current gain, here gain is defined as it is ratio of output to input. Always the gain is defined as it is ratio of output to input. Here this is current gain. So that's why it is output current to the input current. Here output current is IC, input current is IE. So it is IC by IE, IC by IC. So in the case of this common base configuration, IE is approximately equal to IC. I said that IE is approximately equal to IC. That means IC by IE will become unity value, nearly unity. Okay. And voltage gain. Voltage gain is defined as output voltage to the input voltage, VCB to the input voltage VEB. Here, VCB by VEB. Here already VCB is very, very high. So that's why it is very high voltage gain. And after power gain. So here power is voltage into current. So that's why it is unity into very high. It will become high value. Power gain is high. And bandwidth also high. Okay. These are the common base configuration: input impedance, output impedance, current gain, voltage gain, power gain, and bandwidth.